So let's go over some examples and exactly the steps you would determine to figure out, or steps you would go through to figure out the intermolecular forces between certain sets of molecules. So let's start with sulfur dioxide. Okay. So sulfur dioxide, the first thing we want to do is write the chemical formula. So if I look at the chemical formula, sulfur dioxide, again, covalent. So the prefixes tell us something about the molecule. So we know that this is SO2. All right. So that's my first step. My second step is to then come up with the Lewis dot structure. All right. I want to draw the Lewis dot structure, so I follow my Lewis dot diagram steps. Find the total number of valence electrons. Each of these elements or each of these atoms has 6, so it's 6 times 3. So that's a total of 18 valence electrons. Then I set up my skeleton. Sulfur is going to be in the center, so I have S, and then I put my O's on the outside. I create my bonds, and then I make my octets of my non-central atoms. All right, so there we go. We roughly have 16 electrons placed, and I can go ahead and put my total, my extra 2 on the top there. And again, I double checked my octets and my total electrons. I have the correct total numbers of electrons, but I do not have the correct octets because sulfur only has 6. So I'm going to go ahead and I'm going to erase 2 of my valence electrons. And I'm going to go ahead and I'm going to make that a multiple bond instead. So I'm going to put another bond over here. And again, there would be resonance with SO2 or sulfur dioxide, but for our purposes to determine intermolecular forces, the resonance won't matter. All right, so so far we've done the first step, which is find the Lewis dot structure after we found the formula. The second step is to think about the shape. So if we look at this, we have one lone pair of electrons at the top of sulfur, which will result in a slightly bent shape to this molecule, okay? So we have a slightly bent shape to the molecule, which is sort of shown, but let me make it a little bit more clear. Okay, let me make this a little bit more clear. Let me erase these. And then I will make it a little bit more clear, the bent shape that we have. So we've got a double bond here, oxygen, 2, and then 3, 4. All right, so that's the shape of our molecule, okay? The next step is going to be looking at the bond polarity, because if we want to look at intermolecular forces, we need to make sure that the molecule is not polar, or if it is polar, then that would tell us a little bit about its intermolecular forces. So we're going to look at the bond polarity that exists in this particular substance. So if we look at S and O, we know that S has a lower electronegativity. So if I go ahead and draw in my bond polarity, that means that oxygen is going to have the electrons more often, so the dipole points towards oxygen on both sides. Again, doesn't matter if it's a double bond, single bond, the dipole is the same. Excuse me. So what does that mean for molecular polarity then? So the polarity of the molecule would be a little bit different. If I take a look at this, I now see that there would be a molecule dipole, and the molecule dipole would be pointing downward. And what that means is that these oxygens would be partially negative. They get the electrons more of the time. And then the sulfur would be partially positive. All right. So knowing that we have a polar molecule, all right, and then we can look at the intermolecular forces. So the first thing we're going to do is think about what intermolecular force options we have. We have LDF, dipole-dipole, hydrogen bonding, and ion dipole. Okay. Well, the first thing we know is that no matter what, every molecule has LDF. It doesn't matter. As long as it's covalent, we're going to have LDF. So we have 2 covalent molecules, 2 SO2s, that would be attracted to each other. And again, when we talk about intermolecular forces, what we have to imagine is that we have another SO2 this way, for example. Okay. And there might be an attraction between the sulfur here, which is partially positive, and the oxygen here, which is partially negative. That would be the IMF that we would have present. Okay. That's what we're talking about when we're talking about the IMF. Please excuse the incomplete diagram of my SO2. And then maybe we have another SO2 this way. So we have an oxygen here, a double bond, a sulfur here, a single bonded oxygen there. And again, these oxygens would have their valence electrons on the outside. I'm not drawing. And this sulfur would have its valence electrons. And this sulfur with its partially positive would be attracted to the partially negative of another SO2 molecule. Those are the IMFs we're talking about. So this dotted line could represent LDFs because we know that all covalent molecules will be held together by LDFs regardless of what else is present. However, knowing that this is a polar molecule, we now know that in addition to LDF, we also have dipole-dipole. Okay. The next option would be hydrogen bonding. We don't even have any hydrogens here, so we don't have to worry about that. And then we would have ion dipole bonding. That would mean it involves an ionic substance. So we'd have to have two substances. We would have to have an ionic substance and a polar covalent substance. So if I, for example, mix sulfur dioxide with NaCl, then I would have ion dipole forces. The positive sulfur would attract to the negative Cl of the ionic substance. The negative oxygen would attract to the positive Na of the NaCl. But again, I only have one substance, so I can't have ion dipole. Ion dipole involves an ionic substance and a covalent substance. So that would be pulling the ions out of their ionic lattice. So the answer in this case is LDF and dipole-dipole. Those are the only intermolecular forces that are present in this particular instance. Okay, so let's go ahead and move forward to the next example. Okay, so we've got dipole, dipole, and LDF because LDF is always present. Okay, so next one, carbon tetrahydride. We followed the same steps. First thing we're going to do, if we don't have the formula, obviously we're going to need that to determine the Lewis structure. Carbon tetrahydride, tetra, remember tetras, every shape in tetras has 4 boxes, so that's the prefix tetra means 4. So we have CH4. Carbon's in the center, really great central atom because it can make 4 bonds. Every hydrogen's on the outside. So I can go ahead and draw those in. And then I'm going to look at bond polarity, or shape and then bond polarity. So the first thing I want to keep in mind with this shape is that it's very much symmetrical. No matter how I divide this up, we're going to have the same thing on the left as we are on the right, same thing on top as we are on the bottom. It doesn't matter. So regardless if the bonds are polar or not, I know that because this is totally symmetrical, this is a non-polar molecule. Okay? So I know that it's nonpolar because it's 100% symmetrical. Regardless if the bonds are dipoles or the bonds have polarity, it doesn't matter because the molecule itself is nonpolar. Again, polarity is like a tug of war. If the C was a knot in the middle and there are 4 ropes off of it with equal strength people on the end, nobody is going to win that tug of war. So it's exactly nonpolar. Okay, so that fits numbers 3 and 4. So then we start talking about IMFs. Again, 4 options. London dispersion, which we know is always present. So we're talking only about covalent substances because we're talking about between one CH4 and another CH4. So we're going to put LDF because we know it's covalent, and between covalents, you always have LDF. Then we have dipole-dipole. This is nonpolar, so it cannot have dipole-dipole, which means then it cannot have hydrogen bonding. Even though hydrogens are present, hydrogen bonding requires there to be some polarity because it's a type of dipole-dipole. Also cannot be ion dipole because there's no ionic substance present. So in this case, we only have LDF, okay? And if I compared the strength of this LDF to something else, like for example, if I compared it to say CBr4, okay, CBr4, you're thinking, well, it's still 5 atoms, so what's the difference? Still nonpolar, still would make a tetrahedral shape that we see here, still nonpolar. They both only have LDFs, but the difference is CBr4 has more mass because Br has much more mass than hydrogen, okay? So more mass means more electrons. More electrons means stronger London dispersion forces. Stronger intermolecular forces means higher boiling point, higher melting point, more likely to be a solid at room temperature, more likely to be a harder solid than a softer solid. So again, all of these properties that we talk about with covalent substances all come back to these intermolecular forces. The stronger the intermolecular force, that determines your properties, okay? So CBr4, even though it would look very similar to CH4 and it would only have LDFs, it would have stronger LDFs just because it has more electrons, which makes more polarizability, which makes a stronger attraction due to the stronger possible charges that can exist. Okay, so it's really important to remember that. And those strong charges give you different properties like higher melting points, higher boiling points, etc. Okay, So that's what we would get for this particular substance. All right, so again, you see only LDFs. Let's go to the next example. Hydrogen monobromide. Go ahead and pause the video and see if you can do this one on your own. So for hydrogen monobromide, again, I'm going to draw my hydrogen, and my mono means 1, so we just have a Br. Okay, and I'm going to draw my, go ahead and finish my Lewis dot structure, draw my bond, and then I'm going to put my electrons in here. So everything is good if I do that. All right, looking at my polarities, I see that there is a dipole here, and the bond dipole is equivalent to the molecular dipole because there's only one bond. So I can see that it's pulling towards the bromine. All right, so what that tells me is that I'm going to have, obviously, LDF, because we always have LDF with molecular compounds or covalent compounds. That's always going to be a thing. And then if I have another HBr over here, held together by covalent bonds, okay, this Br is partially negative, this Br is partially positive, and the same thing is true here, partially positive for this hydrogen and partially negative for this bromine. So we're trying to figure out what's going to hold these two things together. And what's going to hold them together is the intermolecular force of LDF, but also dipole-dipole, because we have polar molecules, okay? And in this case, we think, well, we have hydrogen, so why isn't it hydrogen bonds? We don't have hydrogen bonds because, again, remember, hydrogen bonds require a FON on both sides of the hydrogen. If we don't have a FON on both sides of the hydrogen to make that FON sandwich, we cannot have a hydrogen bond. So just because we have hydrogens doesn't mean there's hydrogen bonds. This dotted line would represent both London dispersion forces and dipole-dipole. So this thing is held together with, or these particles are held together with 2 intermolecular forces. A little bit stronger than just the ones that have LDF in general. All right, so let's take a look at water. All right, so let's take a look at water. So again, water is H2O. So we go ahead and draw our Lewis dot structure, which is a bent shape because oxygen in H2O has 2 lone pairs on the outside of it, creates a bent shape. All right, so what we end up with, if we look at the polarity, oxygen has a much stronger pull, much stronger electronegativity. So our dipoles point towards oxygen away from hydrogen. Hydrogen ends up with a partially positive charge on both of the hydrogens. Those rarely get the electrons. The oxygen ends up partially negative. So if I draw another water molecule over here, what's going to hold those 2 water molecules together? It's not a true bond. They're not going to bond together. Instead, what we're going to end up with is an intermolecular force that holds them together. Okay? And so what we end up with, the first thing we're always going to write, because we have 2 covalent nonmetal substances, is LDF. The only time you don't write LDF is if you're talking about an ion and a covalent. If you're talking about ionic and covalent, you don't write LDF. So we know LDF is a thing, London dispersion forces, because every set of covalent substances are held together by London dispersion forces due to the temporary random motion of electrons. However, in this case, we also have a polar molecule, right? So we have a molecule dipole pointing towards oxygen. So we know we have dipole-dipole. So we have di-di. And in fact, not only do we have dipole-dipole, but we have these hydrogens that can be sandwiched in between FON. So this hydrogen that's partially positive can be attracted to this oxygen that's partially negative. And it's also, on the other side, bonded to an oxygen. So again, the bond would represent whatever condiment you're going to put on your sandwich, whether that's mayo or mustard or Italian dressing or whatever it is, that's going to hold the hydrogen or the meat of the sandwich to this piece of bread more than it is to this piece of bread, okay? But hydrogen still wants to be part of the sandwich. It's still attracted to that piece of bread. That weaker attraction is the intermolecular force. And in this case, we have hydrogen bonding. So this one has very strong intermolecular forces, okay? Now, just a forewarning, if you put LDF and you put hydrogen bonds, you do not have to write dipole-dipole as well. If you write hydrogen bond, that by definition includes dipole-dipole since hydrogen bond is a type of dipole-dipole. You can add in dipole-dipole as well, but you do not have to. So for this one, I could have written LDF and hydrogen bonds and been totally fine, okay? Because if I write hydrogen bonds, then that by definition includes dipole-dipole because hydrogen bonds only exist if we have dipole-dipole forces. So hopefully that helps work through some examples. Always start with your Lewis dot structure. Determine if you have polarity going on within the molecule, not bond polarity, molecular polarity. Then use that to figure out your intermolecular forces.